This video serves as a review of what we talked about in class before our break, which is how to solve exponential equations using logarithms. So before we get into that review, just to rehash what a log even is, first of all, it undoes is the inverse of an exponential. And an exponential is an equation, a formula, where the variable is the power. So just as a review, here is the exponential form right here, and we see our base b, our power of n, it would normally be in x, equals some value a. And that essentially for us is going to have the same meaning as if we write log. Our base is written as this little number next to the g down low, and then our argument is a, meaning the answer, the value that the exponential would give, equals, and our power is on the outside, equals n. Our calculators are programmed in two bases, base 10, and so if the base isn't written, you're going to assume base 10, and it's also programmed in base e, the natural number, the natural logarithm. And when we mean log base 10, we just write log. We don't write the base. And if we mean log base e, we mean ln. And I'm going to I'll try to remember to capitalize the n just so it doesn't get mixed up with anything else that we know we're talking about, a logarithm. So in order to solve our exponentials, we're going to need our properties of logs. And hopefully you remember that if I'm adding two logs of the same base, so say base c or something, it doesn't matter, I can write that as a single logarithm of the product of those two numbers. So that would be the product rule of logs. Again, the bases have to be the same. And then if we're subtracting, again, whatever our base happens to be, that's the quotient rule. We can write that as a single logarithm and divide them. Now notice I did not write log A over log B. That's the change of base formula. Don't confuse it here with the quotient rule. I'm writing it as a single log. I'm taking the A and dividing it by B and making it the argument, one single argument in one single log, not multiple things right here. The rule that we're going to need is this one, the power rule of logarithms, which basically tells us that this power is going to pop to the outside. So we have b times log of a, whatever our base happens to be. So for solving our exponentials, we're actually going to need just base 10 or just the natural logarithm. So let's go ahead and take a look at our first example. So we see here that we have our exponent, and we need to get this out using that rule. So I'm going to log both sides of this equation. And when I do, now remember, when you're solving equations, you have to do the same thing to both sides. And when I do, I need to pop this to the outside. So I'll have 2x log 3. Now, depending upon your level of class, you might go ahead and type log 3 into your calculator and log 40 into your calculator. For honors and for pre-calc, we're not going to do that until the end. We want to get an exact answer when possible. First thing I'm going to do right here is reorder this. So I'm going to write 2 log 3. And what I want to emphasize here is this is just a number. And then I'll put my x equals log 40. Now, the reason I'm doing that is because this looks kind of similar to something you might have done in Algebra 1, which would be if I had 2x equals 40. And you would know what to do with this step, right? You would divide by 2 and get x equals 20. Now, of course, this is not just 2, and this is not just 40. These are some weird decimal. But that gives us a hint of what we should do. This is just a number, so I'm going to divide by that just a number. I don't know exactly what that number is, and it doesn't matter. So I get x equals exactly whatever log 40 over 2 log 3 is. Now, just as a note, you could rewrite this. You could rewrite this as log 9. And you could say, all right, I have log 40 over log 9, which is the change of base for log base 9 of 40. Which is okay. I mean, but we don't need that. I'm just saying you could do that if there were a situation to arise that you needed to. So this is fine. We're okay with this. This is the exact answer, and we're going to keep it like this. We're not going to do any further changes. However, sometimes we need a decimal answer. So we're going to actually type this into our calculator, and make sure when you're typing it into your calculator that you emphasize the top, the numerator in parentheses, and the bottom in its entirety in parentheses. That way your calculator does things in the way that you mean. So I'm just going to take a moment to type that in. And I get x is approximately, I'll just go ahead and do 3 decimal places. And the reason we want to keep decimal places to a relatively higher number is because, not a higher number, but a higher number of them is because when you're dealing with exponential equations, like those decimal places end up mattering, especially if you're talking about investments over a long period of time. Those extra decimal places could mean the difference of $100 or something like that, something significant. So we want to keep them. Okay, so let's go on to our next example, and I would encourage you to check this on your calculator. Make sure you're getting the same things that I am. That way, you know that you're typing things into your calculator correctly. All right, so this example being a little bit more difficult, but we're going to follow the same pattern. So again, I see that my variable is the power. So I'm going to need to log both sides of my equation. And when I do, this entire group is going to pop out. And notice I'm putting it into parentheses. And I'll emphasize why that's the case in a moment. And this whole thing is going to pop out. And then let's go ahead and talk about why this is an important distinction. If you were to write, say, 2x minus 9, and then have your log 6, well, that's completely different. This would mean 9 times the log 6, whereas we mean the quantity 2x minus 9 times log 6. So the difference being here that if I were to write this, this is not the same as writing this. Because this 3 would just multiply that 9 and I get 27, and then this 3 would distribute into here and I get 6x minus 27. And I mean the second thing in this situation. Okay, I don't really want all this here, so I'm going to go ahead and delete all that. So hopefully you understand that distinction. Now, we would distribute this 6. So over here, kind of in this top corner, I'm going to write a similar situation, but it's not going to be exact, of course, because I have log 6 here. And then if I have 3x minus 40, and then I have a 9 right here. All right, so let's think what we would do if we were in Algebra 1 and we had this situation. Well, we distribute the 6 and we distribute the 9. And we'd get 2 times 6, x, minus 9 times 6, equals 3 times 9, x, minus 40 times 9. Which does give us 12x minus 54 equals 27x minus 360. Okay, so that gives us a clue of what we need to do here. We need to take all of this and distribute it to each of these things, just like we would have done, say, in Algebra 1. So I'm going to do that, and as I'm doing it, I'm going to order things such that I'm emphasizing that this 2 times this is just a number that is a coefficient of x. And I also want to draw a distinction, I'll do it down here, that 2 log 6, x like this, is not the same as saying 2 log 6x. In this second one, I'm logging the quantity 6x, and x is in the argument. which is completely different than what I mean over here, which is this quantity is some number multiplied times the x. All right, let's distribute this. So 3 log 9 x minus 40 log 9. Okay, now let's go back over here to the right and kind of think, what would we do now if we were in algebra 1? And that would be get x to one side. And I'm just going to choose, for no particular reason, to get x on the left. I would do something like this, right? And then I would get, say, negative 15x. And then I would add the 54, right? So I'd add 54 to the other side. And that'll give me negative, 303? So I'm going to do those steps over here. Now, how did I get this negative 15x? That's going to be important. So let's do that discussion right here. How do we get this? And maybe it's kind of obvious to you that, well, those are like terms, and so we're just combining them. But the why we get that's very important to understand why what we're going to do over here is going to work. So we have 12x minus 27x, right? And then what's really happening is we're taking this x and we're factoring it out. And now we see we just have these numbers right here, and we just actually subtract them and get negative 15 times the x. So that step of factoring, which we skip a lot, and it's okay to skip it because we're doing a shortcut here. We identify these like terms, but when we lose the reason why it works, it's harder to see why what we're going to do on this log equation works. So we want to remember that the reason that combining these like terms is working out is because we're factoring out the variable and then combining. So we're going to do the same thing. We're going to get x to the left. You could get it to the right. I'm just going to choose always to get it to the left. That way our answers can be consistent. As in the signs will end up being the same when I check your homework, say. So let's subtract the 3x, or 3 log 9x. So I subtracted this over, and I'm going to add this thing over to the other side. See, I added this, just like I would over in this other equation. So now I see, now if you were, say, in not an honors class, you would probably have way up here typed log 6 into your calculator, typed log 9 into your calculator, and then distributed some weird decimal, got lots of decimals. We're not doing that here. We're waiting until the end. So we're going to factor out the x. So we're going to write 2 log 6 minus 3 log 9, and we factor out the x. And then we'll leave the whole right-hand side the way it is. And technically, since these are the same base, we could bring in the negative 40, we could bring in the 9 as exponents, and combine them. And write them as a single log, but we're not going to bother with that. Now we see, what would we do next up here? Like at this step, what would be the last step? And hopefully you're saying, well, divide by negative 15. That's exactly what we're going to do. We're going to divide by this entire group right here. And this just shows why it's very important to be precise with your parentheses. Because if you're not, you're going to end up actually getting really confused, and be very neat with your writing so that you're not mistaking numbers for things that they don't represent. All right, this is the exact answer. Okay, so x equals that stuff. So let's check and see, well, what is x approximately? So take a moment, type it into your calculator, and see what happens. And we should get approximately 23.856. Now, please, if you're in Algebra 2, pre-calc, whatever it may be, make sure you round correctly, all right? When you type this in exactly the way it appears, and you round correctly, this is what you get, okay? Don't misround. All right, let's go on to another example. So that last one we just did, is about as difficult as these will get on our level. Notice this one has an e. So what are we going to do different? Well, we've been logging base 10, but I see that my exponential portion is an e, which tells me I want to log base e, which actually, as scary as this may look, actually turns out to be really, really easy. This is the easiest situation that you could possibly get at our level. So I'm going to be writing ln. And something we want to remember is if I would log base 10 of 10, I get 1. And if I log base 5 of 5, I get 1. So if I log base b of b, I get 1. That's always going to happen. So I'm going to be natural logging, that is base e, of an e, which means I'm going to get a 1 into this mix, which is going to be what's going to make this easy. So the first thing that we're going to want to do is we see this like minus 12, and we're going to want to deal with that. Also, we want to isolate this portion first. Don't be logging right now. Like when you take a look at the ones that we just did, that was our first step. We logged both sides to pop the exponent out. But the problem is we have this like little extra like plus stuff here that we don't want. Okay, so apparently I'm on the wrong thing, but that's okay. So we have this, yeah, I wrote it on the wrong slide, but that's okay. So we don't want it. Yeah, that's not there. All right, so we isolate this. We're going to add the 12. All right, so that gives us 35. And then we have 5e 9x plus 6. All right, we need to isolate this part, so we're going to divide by 5 next. So we get 7. Then we have e 9x plus 6. Now from here, what do we do? Well, we're going to natural log both sides of this equation, only after we've gotten the e alone. So now this whole group is going to pop out. And then we have natural log e. But the natural log e, ln e, is 1. So this is times 1, so it doesn't matter. Now we need to remember the most common mistake I see with these is actually natural logging the left, but not the right. You need to log both sides. So this is just a 1. So we're going to have ln 7, and I have 9x plus 6. I'm going to subtract the 6 and divide by 9. So I have natural log 7 minus 6 divided by 9. All right, so what is that approximately? We go ahead and we put that into our calculator. Our ln key should be where the e is. Now, not the capital E as in the... This is going to be confusing to say. Your calculator can type letters on it. We don't want that. We want the little e with the x, and that should also be the ln key. So we're going to natural log 7, subtract the 6, and divide by 9 at the very end. And we get x is approximately negative 0.4504. So if I'm keeping 3 decimal places, I would need to write that 0 to emphasize I actually rounded to that spot and not the 100th spot. Okay, so this is our answer. Which, by the way, if the directions say round to the nearest thousandth, and you get a 0 in thousandth place, you need to write it, like, to show that you actually rounded to that spot. Okay, so only 2 more examples left, and of them, one of them has a trick, and that's going to be this one. So let's go ahead and take a look at this example. So again, we need to isolate the e. We want to get this alone. So I'm going to subtract the 18, and that's going to give me 22. And then I have negative 2 e to the 5x. I'm going to divide by negative 2. Again, isolating this e. and then I get negative 11. And at this step, we're gonna find a problem. So we're gonna natural log e 5x, and we're gonna natural log negative 11. And you might be tempted to just keep on going. So I'm gonna do that. The 5x comes out. I have ln e. Again, ln e. This is just 1. So that's 1. So 1 times anything is that thing. Equals natural log negative 11. And then I have 5x equals natural log negative 11. I should have had this in parentheses. Divide by 5, and we might be very tempted to say, all right, we're good. All right, if we are, which if the directions were to say find the exact answer, as often in my homework they will, you might be tempted to just stop there, but even if you're not told to, it is definitely worth checking this out. So when I type it into my calculator, I do get an error. And that should flag us. That doesn't mean come up to me and whine about it. That means we have a problem. We can't log negatives. That's not going to work out. And the reason being is it's the inverse of an exponential, right? So if I were to look at a graph to make this make sense, if I were to graph, say, any random exponential, it will generally look like this as long as our base is positive and our exponent is positive. That we got this situation. Now in inverse, which is what a log is the reflection of this over the line y equals x. So we generally get something that looks like this. And notice something, that while the exponential has both a positive and negative portion as far as the value of x, like x can be negative and then x can be positive. If I take a look at this one, which this would be representing the log, well, this graph only has positives and it has no negatives. There's nothing over here. We can't log. This is why we're not going to be able to log the negative. So, or even 0. So that's why we're going to have an error right here. And so rather than write all this, at this step, way back here, right when I would log a negative, I would say, wait a minute, I can't do that. And so I'm going to say there's no solution right here. I would just stop at that step. Okay, so since that was a bust, let's try one that will not be. And that'll be this one. So I just made a minor change and made the 40 negative. So now when I subtract the 18, I get negative 58. I'm going to divide by negative 2. And that gives me 26. No, it does not give me 26. Am I crazy? The answer is yes, I am. That does not give me 26. That gives me 29. Get in the right mode. Deselect. It thinks I'm trying to select that. All right, 29. All right, e to the 5x. Now I'll log both sides. So I have 5x, natural log it though, e. Natural log both sides. I could just get a number right here. Natural log e is 1. So I have 5x equals ln 29. I'm going to divide by 5. So this is my exact answer. And then we will go to our calculator to go ahead and find an estimate. 0.673 approximately. Okay, that basically concludes our lesson on solving exponentials. So good luck on your homework.